Welcome to Engineering Studio with Dr. Mohammed Tahir. In the previous video, we have discussed about the types of foundation. In this video, we will discuss about the limit states, or failure modes of concrete footings, and design considerations. So limit states. Limit states define the failure mode and the capacity of footing corresponding to each limit state is determined from the mechanism of failure. So limit states define the failure mode, and capacity of the footing corresponding to each failure mode or each limit state can be determined by using the mechanism of failure. So based on the failure type, we can calculate we can find out the capacity of the footing. So while designing the footing, all types of failure modes need to be investigated and safety is ensured at service loads. So let's see what are the limit states in case of concrete footings and what are the design considerations corresponding to those limit states. So first one is soil failure or differential settlement. Our foundation can fail either because of failure in the soil. Soil can fail in shear, or there can be excessive settlement, or there can be differential settlements. So because of the differential settlement, our structure or our foundation can fail. Okay, to avoid this type of failure, we need to play with the size and type of footing. So we can change the size to avoid the soil failure, as well as we need to change the type, or we need to properly select the type of footing to avoid the differential settlements. The next possible failure is one-way shear failure in case of footing. So to avoid the one-way shear failure, we can play with the thickness of the footing slab, thickness of the footing slab. So to increase the capacity against the shear failure or one-way shear failure, we need to increase the thickness of footing. The third failure mode is two-way or punching shear failure. So again, to avoid this type of failure, we can play with the thickness of footing. Flexural failure or failure due to bending. So to avoid this type of failure, we can play with the thickness of the footing, as well as we need to design the reinforcement for footing slab. The fifth type of possible failure is bearing failure at the base of the column. So this can be avoided by dowel reinforcement, by providing dowel reinforcement, or by increasing the strength of the concrete in column. The sixth type of possible failure is bearing failure in the footing slab. So this can be overcome by providing the dowel reinforcement. And the seventh type of possible failure is slippage in the dowel bars or column reinforcement. To ensure the safety against this slippage, or to avoid the slippage, we need to provide the minimum development length. Okay, first of all, soil failure or differential settlement. So one by one we will discuss all those type of failures, and we will see how we can ensure the safety against those failure modes. So settlement becomes excessive if the applied loads is larger than the capacity of soil. So if the applied load is more than the capacity of soil, or the contact pressure under the foundation is more than the capacity of soil, so in that case settlement becomes excessive, or the soil can fail. The size of footing should be such that the gross contact pressure under the footing due to service loads, including backfill, surcharge, weight of footing, should be less than the soil allowable bearing capacity. So the gross pressure under the footing should be less than the allowable bearing capacity. So if we satisfy this condition, in that case our structure will be safe against the soil failure. To avoid the differential settlement, we can play with the shape as well as the type of footing. As we have seen in case of types of footing in the previous video, so we have seen if there is a possibility of differential settlement, we can use combined footing, strip footing, or raft footing. So here in this figure we can see if the whole structure settles, so in that case our structure will not have any crack. But if it settles linearly from one side to the other, the settlement is linear, here the settlement is more and here the settlement is less, So in that case, there is a possibility of overturning. And this building will overturn when the centroid of the mass of this building crosses or lie away from this bearing area. Otherwise, this will remain stable. But the most critical is if the settlement occur in some part of the building. So in that case, the structure can collapse or there may occur large cracks in the walls. So if there is a crack, inclined crack or vertical crack in the wall, so that may be because of differential settlement or settlement of the some part of building. Okay, next is one-way shear in footing. So it is a beam type shear leading to diagonal tension failure. So just like beam, we have a failure, diagonal tension failure in slabs. So applicable particularly to strip footing. So this one-way shear is most critical in case of strip footing or the footings below the load-bearing walls. A potential diagonal crack extends in a plane across entire width of the slab. So a crack will appear across the whole width of the slab. So this type of crack, the inclined crack, will appear at a distance d from the face of the column in the whole width of this slab. One-way shear crack appear parallel to the side of column at a distance d from the face. So the critical section is considered at a distance d from the face of the column. So we consider the critical section at a distance d from the face of column in case of one-way shear. So the maximum shear or the maximum applied one-way shear in footing can be calculated by multiplying the contact pressure with the cantilever span beyond the critical section. So this is the cantilever span beyond the critical section. If we multiply this span with the QU, the net contact pressure, so we get the total applied one-way shear on the footing. That will cause a diagonal tension crack in the slab in the whole width. So the capacity of footing against one-way shear is given by this equation specified in ACI code. So here B is the width of slab, the width of this slab, and D is the effective depth from top of the slab up to the center of the reinforcement, effective depth. So to ensure the safety against this one-way shear, this condition should be satisfied. The capacity of the slab against this one-way shear should be more than the applied shear. So if this equation satisfied, then our foundation will be safe against this one-way shear. The next is two-way or punching shear in footings. So the shear acting all along the perimeter of a column can punch the column in the footing slab and is called two-way or punching shear. So here we can see the diagonal crack appear on both sides or on the four side of the column, and the column will be punched out of this slab. And this appear all along the column. So this type of shear is termed as two-way or punching shears. The punching shear failure or two-way shear failure is critical around the column perimeter at a distance d by 2. So in case of two-way shear, we consider the critical section at a distance d by 2 from the face of column. So here the distance from the face up to this critical section is d by 2. D is the effective depth of slab. And the applied shear can be calculated, applied two-way shear can be calculated by multiplying the contact pressure under this foundation or under this footing slab multiplied by the area of footing outside the critical parameter. So if we see QU multiplied by, this is the total area minus the area of footing inside this critical section. So this area, this unshaded area. So if we subtract this unshaded area out of this total area, we will get this shaded area, and the load acting on this shaded area will cause two-way or punching shear. Okay, next is how we can calculate the capacity of the footing slab against the two-way shear. So we can calculate the capacity or the strength of concrete against the two-way shear by using this formula. This is these three formulas, and the lesser out of these three will be considered. So these formulas are specified in ACI code, and we have studied these formulas, or we have studied the concept of two-way shear in detail in case of direct design method. So here if we see, we have B naught and D. So B naught is the critical section perimeter, D is the effective depth, B is the ratio of longer to shorter side of the column, and alpha is a factor which is 40 for interior columns, 30 for edge columns, and 20 for corner columns. So by using these three equations, we can estimate the capacity of concrete against the two-way shear. And here lambda is a factor which accounts for the lightweight concrete. In case of normal strength concrete or normal weight concrete, its value is 1, but for lightweight concrete, its value may be 0.75, or we can select the value if we know the density of concrete. So depth of footing should be such that, or we need to satisfy this equation, so which is the shear capacity of the concrete slab against punching shear should be more than the applied punching shear. So to satisfy this equation, we need to play with the thickness of slab. So we need to select the thickness such that this equation or this condition is satisfied. Okay, next is bending moment in footing. So to design for the, or to ensure the safety against the bending moment, we need to play with the thickness as well as with the reinforcement, or we need to provide the reinforcement in the footing. So footing slab of isolated or strip footing act as a cantilever beam subjected to uniformly distributed load. So this slab will be considered as a cantilever beam, and it will be subjected to a uniformly distributed load. So flexural crack appear parallel to each side of the column close to the face of column. So the critical section will be close to the face of the column. So like over here. So in case of footing of concrete columns, so here we have a column which is of concrete as well as the footing is also of concrete. So in that case, the critical section will lie at the face of the column. But in case of masonry walls, the critical section will be inside this wall. If the width of this wall is B, then this critical section will lie inside at a distance B by 4. And in case of concrete footing, under this steel column, and this steel column have a base plate, steel base plate, so in that case, the critical section will be at a distance S by 2 from the face of the column, and S is the projection. So if this is the column and this is the base plate, and here we have a footing, so this projection of this base plate is S, and the critical section will be at a distance S by 2 from the face of the column. So these are the critical section for flexure. Okay, to design against the bending moment, a unit strip of slab is considered for design spanning up to the critical section. So to design for the flexure, we consider a unit strip. Unit strip means a strip having width of 1 meter, 1 millimeter, 1 inch, or 1 feet. So the bending moment for longer steel can be calculated mu time QU, the applied load, times L minus C1 by 2 square over 2. So we need to understand from this figure. So in this direction, the critical section will lie at the face of the column. So this will be the critical section, and we need to consider this unit strip for the design. So the width of this strip will be 1 meter if we are using SI units. And if this is the width of the footing and this is the length of the footing, so the span of this cantilever beam or this cantilever strip will be equal to L by 2 minus half of the column width C1 by 2, or we can write L minus C1 divided by 2. It's over here. So similarly, span in shorter direction can be calculated. So here this is the design strip, and the span, this one span will be equal to B by 2 minus C2 by 2, or B minus C2 by 2. So in this way we can calculate the span. So we need to calculate this much distance. So this, if this distance is L, so the bending moment will be equal to Q time L by 2 or Q time L square by 2. So this is actually Q, this is span and its square by 2. This is Q span and its square by 2. So uniformly distributed load under this unit strip multiplied by the length of this unit strip or the span of this unit strip multiplied by L by 2. The centroidal distance up to the critical section. Flexural reinforcement should be such that the nominal capacity or the design capacity of the footing against flexure should be more than the applied bending moment. So we need to provide the reinforcement to increase its flexural capacity, and the flexural capacity of the section should be more than the applied bending moment in both the direction, shorter as well as longer direction. And this mu is the bending moment, applied bending moment at a critical section, which is normally at the face of the column in case of concrete columns footing. Okay, if bending moment in a column produces uplift on one side of the footing and soil above prevents this uplift, top steel in the footing must be provided for bending moment calculated based on the weight of the soil. So this is the case if we have a concentric load, so we need to provide the footing reinforcement at the bottom only, because in that case the bending moment will try to, or the soil pressure will try to uplift these sides. So because of the soil, the bending will be in this direction, so we need to provide the reinforcement at the bottom only. But if we have a footing and load is acting at some eccentricity, or there is load as well as bending moment, and this bending moment try to uplift the footing, so it try to uplift the footing like this. So on this side if we have tension, and the footing is uplifted, but the soil above this footing prevent this uplift. So in that case the scenario will be like this. So we have a column, the pressure is acting from the top. So this moment try to turn it in this direction, but this pressure of the backfill as well as the surcharge prevent this uplift on this side, and as a result the scenario will be like that, there is a pressure from the top. So in that case it will try to bend it in this direction, and the bending will be in this direction. So we need to provide reinforcement at the top. So we need to provide the top reinforcement as well in this case. So next is about the distribution of footing steel for flexure. So if we have a square footing, so in that case the distribution of the reinforcement will be uniform whatsoever is the area calculated for this direction. So we need to calculate the spacing of the footing based on the area of the reinforcement and then provide at equal spacing. Similarly for this direction. But if our footing is rectangular, so in that case the longer side reinforcement will be provided at uniform spacing, but for the shorter direction reinforcement we need to provide more reinforcement in central band. So in this portion we need to provide extra reinforcement or more reinforcement, but on these edges we can reduce the spacing or reduce the area of the reinforcement. So what we will do, we will calculate the complete or the total area of reinforcement required for this direction, for shorter direction or shorter reinforcement, and then we will provide this much fraction of this total area to this central band, and the remaining will be provided at the edges. So the reinforcement in band width, which is equal to B, this B, so this band width from here up to here, it is equal to B by 2 is plus B by 2, so it is equal to B, width of the footing. So reinforcement in band width over total reinforcement in shorter direction means the ratio or the fraction of the reinforcement to be provided in the bandwidth out of the total reinforcement should be equal to 2 over beta plus 1, and beta is the ratio of longer to shorter side of footing. So for example, if we have a square footing, so in that case beta will be equal to 1, and this fraction will become 2 over 1 plus 1 is equal to 1. So it means reinforcement in bandwidth should be equal to total reinforcement. But if we have this beta is equal to 2, so in that case it will be 2 over 2 plus 1, it will be 2 by 3. So what it means? The reinforcement in bandwidth will be equal to 2 by third of total reinforcement. So 2 by third of total reinforcement will be provided in this much area, and the remaining 1/3 will be provided in the remaining area on both sides. Next is bearing failure at the base of column. So to ensure the safety against bearing failure at the base of column, what we need to do? So the load from column to footing is transferred by two means: by direct bearing of column or concrete over the footing, and by force in dowels or column reinforcement which across the interface between column and footing. So the total load, the applied load, is carried by the concrete as well as this dowel reinforcement or the reinforcement of the column which transfer or which cross this interface. So here if we see the column at this stage is resisting the load some portion by concrete and some portion by steel. The total load of the column is resisted by this concrete as well as steel. But as we go downward near to the interface between column and the footing, if the reinforcement of column is terminated at the face of the footing, so the load carried by this steel will continue to decrease. So the load carried by this steel is continue to decrease, and it will become 0 at the face of the footing. And as a result, the total load will be resisted by the concrete. So the fraction or the portion of the load which is resisted by the concrete continue to increase, and at the face of the support most of the load or the total load is carried by this concrete. If we don't have any dowel reinforcement, then the total load at this point or at the interface of the column and footing will be resisted by the concrete. So in that case our concrete should be strong enough to bear the applied load, or otherwise we need to provide this dowel reinforcement so that some part of this load should be resisted by the dowel reinforcement. So it can be resisted by the concrete and the dowels. So if dowels are not provided, then the whole load at interface will be resisted by the concrete only. To avoid failure at this interface, either the strength of concrete should be enough to resist the load or dowel reinforcement should be provided to resist the load. So to make this structure safe or to safeguard against the bearing failure at this position, either we need to increase the strength of concrete so that the concrete alone should be able to resist the load of column, or otherwise we need to provide this dowel reinforcement so that the load which was carried by the reinforcement in the column should be transferred to the dowel reinforcement, and concrete should resist the same load that it was resisting in the column at the interface of the footing. Okay, the bearing strength provided by the column concrete is given by this one. The strength provided by the concrete, it is equal to phi 0.85 Fc prime Ag, and here phi is 0.65. In case of compression, we consider this factor 0.65. And bearing strength to be provided by the dowels is equal to PD, and it is the difference or the net of the applied load. So Pu minus the load resisted by the concrete. So Pu is the total load of column, and phi PNC is the load resisted by the concrete. So the remaining portion will be resisted by the dowels. So the area of steel required for the dowel is equal to load resisted by dowel divided by phi Fi. So this is simply sigma is equal to P over A. So we just need to rearrange this equation. A is equal to P over sigma. So at the design stage we consider the limit state, and we consider that our reinforcement should reach at its yield strength. So the area required will be equal to Pu applied load divided by the Fy, and we multiply it with the reduction factor phi, which is 0.65. So in this way we can calculate the area of steel required to resist the additional load, or area of dowel reinforcement to resist this PD, the load that must be resisted by the dowels. So the ACI specifies that the minimum area of steel required for dowel should be equal to 0.005 times gross area, and AG is the gross area of the supported member or area of columns. So we need to provide 0.5% reinforcement for dowels, or the higher value calculated from here. So next is bearing failure. Next is bearing failure of footing at the base. So if our column is strong enough and it doesn't fail at the interface, there is a possibility that the concrete of the footing may fail in the bearing. So we need to check the concrete of footing against bearing. So the bearing strength provided by the foundation concrete can be calculated by using this formula, which is 0.85 Fc prime time area of the column multiplied by A2 over A1, and it should be less than 2 times of 0.85 Fc prime A1. Here A2 is the area of footing effective in resisting the bearing stress at a certain depth inside the footing, calculated by taking distribution of 1 vertical and 2 horizontal. So we consider the distribution of stress inside the footing by 1 vertical and 2 horizontal. So if the case is like this, the footing is sufficiently large and this tributary area lies within this footing, so in that case the area will be considered at this location, at the bottom of this footing. So if this is H or D, so we will go in this direction equal to 2H, and in this direction 2H, and similarly 2H on all 4 sides. So we can calculate this area at this level. So the total will be 4H plus the dimension of the column. For example, it is C1. Similarly, it will be multiplied with 4H plus C2. So it will give us A2. But if this column is close to one edge, so in that case, if we consider this distribution 2:1, so we will reach up to the edge of this footing at a certain depth. So at this depth, we will reach at the edge of this footing, and the area at this level will be considered. So here it is more clear. We have a column and its distribution is considered like this. So at this level we have reached at the one face of the footing. So the area at this level will be considered, and if we see in the plane, so it will be like this. So whatsoever is this much distance, this will be considered on this side, as well as on this side. So it will be considered on 4 sides. So what we need to do, if it is L, so (2L plus C2 times 2L plus C1), it will be equal to A2. So to simplify this, or to avoid the complication, what we need to do, we can see our column in plane. For example, we have a column in plane like this. So if our column lie over here, so we need to see all these edge distances. For example, this is L1, this is L2, this is L3, and this is L4. And we need to compare these L1 to L4, and these should be less than H. For example, so it should be less than 2 times H. For example, L1 is the least of these 4, so L1 is less than 2H. It is less than 2H, so we will consider L1 as the governing factor. So in that case, our A2 will be equal to, so we will consider L1 on this side, so our area will be like this much area. So on all 4 sides we will have the projection from the face of the column equal to L1. So this dimension will be equal to L1, C2 or C1 and L1 from here up to here and then here. Similarly, on this side we will have L1, L1 and C2. So we will have 2L1 plus C1 times 2L1 plus C2. So it will give us A2. But if the case is like this, that we have column over here, this is L1, L2, L3 and L4. So L1 to L4 are less than equal to 2H, but here these are L1 to L4 are greater than 2H. So in that case we will consider this 2H, and A2 will be equal to, so in that case we need to consider this 2H. So 2H will be over here. So from here up to here, this will be 2H, this will be C1, this will be 2H. Similarly on this side, this is 2H, this is C2 and this is 2H. So it will become 4H plus C1 times 4H plus C2. So from here we can calculate A2. So we just need to consider the least projection and then compare it with the 2H and then select the least value out of these two. Least projection and 2H, the smaller value out of these two, and then put it over here. Okay, once we have A1 and A2, we can easily calculate this, the load resisted by the concrete in case of footing, or the bearing strength provided by the footing concrete. So the bearing strength to be provided by the dowel in footing concrete is equal to PD. It is again the applied load on the column minus the strength provided by the footing concrete. And the area of steel required for the dowel is load resisted by the dowel divided by 5 Fy. So from here we will get the area of the dowel reinforcement, and based on the area we can select the number of bars, and the minimum area should be more than 0.005. If this area is less than 0.005 AG, so we need to consider this value. So in this way we will provide the dowel reinforcement. So the next is general procedure for footing design. So this will be covered in the next video.